Hi. In this short video, I wanted to give an additional explanation towards the lab number 1, the torsion pendulum. The explanation of the differences between the linear harmonic oscillator and the torsion pendulum, which is also in a sense a harmonic oscillator. So the question I frequently get is on the difference between the differential equation that describes the linear harmonic motion and this equation that describes the torsion pendulum. So let's go through this very quickly again. So for the linear harmonic oscillator, we have a mass attached to a spring, and there are two parameters characterizing this system: the spring constant K and the mass of the block, okay? So the system is frictionless, so the only force acting on the block is the force of the spring, right? So the equation of motion is written here. This is a differential equation. Essentially, this is Newton's second law, right? So this is mass times the acceleration. X is the only coordinate in this case. So this is the second derivative of x with respect to time. So x in this case is a function of time. X is a function of time. This one is the spring force, right? So what is written here is essentially the Newton's second law. Ma, mass times the acceleration, should be equal to the net forces acting on the mass, okay? So Ma in this case is mx double prime. This is the second derivative with respect to time, equals, and the only force acting on the block in this problem is the spring force, which is minus kx, okay? So the k is the spring constant, x is the stretching, the amount of stretching or compression of the spring. So this is simply the force for the small compression or extension of the spring, okay, in the linear regime. You can rearrange it and you get this, okay? Now for the torsion pendulum, what we have is a mass, a rectangular block in this case, which is attached to the spring, to the string, metal wire, and suspended from this point. Okay, so we have vertical string and a massive block attached here. So the block has a mass m and these dimensions, the width a and the length b. Okay. So we were saying that, okay, this block can be characterized by its moment of inertia, I, which, well, for this shape, it's m over 12 times a square plus b square, right? So what happens here is that when you excite the block by turning it slightly and releasing, it will start oscillating by rotating in the horizontal plane, in the plane perpendicular to the string, right? And these rotations are caused by the torque that this elastic string exerts on the block, because it's sort of rigid. It has certain rigidity, the string, and it will try to return the block into the equilibrium position. So that causes this oscillations, rotational oscillations of the block. Now, we wrote this equation that describes this motion. This is the same type of differential equation as for the linear harmonic oscillator, right? So the moment of inertia of the block times theta double prime. So theta here is the angle of rotation. So if I draw this line, this dotted line, this is the axis going through the, parallel to the axis of the block. So as the block rotates, this dotted line will be changing the angle in the basal plane, in the plane perpendicular to the string. And this theta angle can be used as the coordinate in this case to describe the motion of the block. So theta here is in full analogy to x for the linear motion, okay? Then it goes like this, plus k, which is a torque constant. It's kind of analogous to the spring constant in that problem, times theta equals 0, okay? So the question I was getting from students is, how do we get to this point? Why are we using moment of inertia instead of the mass and so on? So the best way to answer this, this question is to consider a problem more simple than this, okay? So let's consider a point mass rotating in a circle. Okay, so now we're considering the axis of rotation. Axis of rotation. And let us consider a mass here, a point mass, M, which is at a fixed radius R away from the axis. And this mass can be rotating in this horizontal plane, rotating like this, around this axis, okay? So if I look at the top view of this situation, I will have a center of rotation, and then I will have a mass basically that can rotate around this circle, okay? So I hope you can see it there. So this radius is R. This is the mass M that can be oscillating back and forth around this circle. Okay. Okay. So this is radius R. So let me consider a small increment in this angle theta. Okay. So let's say this angle here is d theta. Okay. This increment in the angle d theta will correspond to some small increment of path along the circumference that the mass is going through, right? Let's call it dl, okay? So dl corresponds to this increment in the angle of rotation. So I can write down that dl, the increment of the path, this one here, of mass going along the circle, dl, is the radius times d theta, right? It's the radius, which is fixed, times the small increment of the angle d theta. Okay, so let's calculate the velocity, the corresponding velocity of that motion of the mass going along the circumference. So that velocity, which in our case, by the way, is not going to be constant because we're not talking about constant, I mean, rotation with a constant linear speed, right? We're talking about oscillations like this, back and forth, rotational oscillations. And therefore, this V itself is not a fixed value. It's going to be itself a function of time. But anyways, V by definition is going to be dl dt, right? R is a fixed constant in this problem. So plugging this to here, we get R d theta dt, right? So, so this is velocity. Now, what about acceleration? Then acceleration A of the mass is by definition dv dt, right? So dv dt is differentiating this again. We get R, basically the second derivative of theta shows up here. like this, right? So that's the acceleration. Can I erase something? Oh, I still have space here at the bottom. Okay, so let me keep writing here. Then what I will write is the following. So I need to write the Newton's second law. Ma equals the force, net force acting on that point mass, right? So Ma is this, so mr theta double prime equals to what kind of forces do we have here? So the question is, why is the mass returning and oscillating back and forth? So it's returning all the time, is deviating from the equilibrium point. The reason is because there must be some torque applied to this mass. In other words, there is actually a force F, which is which depends on the coordinate. In a similar way that here in the spring problem, you have this returning force applied to the mass every time the mass has non-zero x, right? In the same way, there is a force acting on the mass here, and the force comes from the rigidity of the string, which is trying to return it from the whenever it's deviating from the equilibrium point, it's trying to return it back into the equilibrium. So this force is this force. Right, so let's leave it as F so far, right? The force F. Okay. Then let's multiply this equation by R on the left-hand side and right-hand side. Okay, so what you're getting then is this mr squared times theta double prime equals RF. Okay, RF. But what is RF? R is always perpendicular to the force. So RF is something that we called a torque, right? It's the moment of force, or it's a torque. And this prefactor here, by definition, for the point mass, is the moment of inertia. Moment of inertia. Now, the force, right? So again, we can rearrange, so we can state that the moment of inertia times the second derivative of I, the force is essentially minus, the force is this force, can be defined as minus this equals to that, right? So force equals minus, wait, what I want to write is this. So RF, the torque is K times theta, okay? So that's the definition of torque constant in this case. The torque is linear with the angle of rotation, theta. So they're directly proportional in the linear regime, of course, for the oscillations that are small in amplitude. So that's the definition of torque constant here. And that's why we can rewrite it as actually with the minus sign. Minus K theta, like this. So torque equals the torque constant with the minus sign times theta. And that's why you're getting this relationship by rearranging to the left-hand side. Plus k theta equals 0. So you are getting an equation which is fully equivalent to the this equation for the harmonic oscillator. In the linear case, for the linear motion, so every time you're dealing with rotational motion, not necessarily harmonic oscillator, but different type of motion, if you replace masses with moments of inertia, you replace the linear coordinates with angle, and you replace all the forces with their corresponding torques, and then you can write the differential equation of motion in terms of all those variables. They will look, the form of those equations will look exactly the same, the type of those equations, as the corresponding equations for the linear motion. So that's a short answer why here we have a moment of inertia instead of the mass, and here we have torque constant, and why we use angles as our coordinate instead of linear coordinates.